Mathematical modeling, first order difference equations. A couple of words about mathematical modeling. In this we fix parameters to work on other parameters. So for example, there may be a number of parameters affecting something. An aircraft flying through the air is affected. Its speed is affected by the mass of the aircraft, the thrusts of the engines, the existing wind conditions, the existing density of the air, which is related to the temperature, and so on. Now in mathematical modeling, we fix certain parameters so we can work with others to look at behavior of factors. The more complex mathematical modeling becomes, the more we introduce further parameters, and that's when we need to use computers to do it. Very clearly a useful tool in this modern age. Now the first order linear difference equation is the most basic form of mathematical modeling. You should recognize this. This is the formula from a recursive sequence where any term is defined by its preceding term or terms. In this case, xn is equal to alpha times the previous term, xn plus 1 equals alpha times xn, the previous term, plus beta, where alpha and beta are constants. Notice here n equals 0 upwards, counting numbers or whole numbers, not from 1 as we usually do with sequences. And very useful, but not going into the reasoning behind it at this stage. Here is a formula to be able to solve that equation there to find the value of any xn. So knowing the formula we could find t20, t56, etc. But clearly we do need to know the value of x0, the first term. Same in recursive sequences. Let's use it now. If you have a look at this, let's apply it to a recursive sequence. There's the recursive formula. As usual, we're given the first term, and then any term is defined by its preceding term, twice the preceding term plus 5. Little warning, as mentioned before, we need to allow for the fact the solution formula in this case refers to A0, the solution formula, x0, a0, but in this case it's a1. So if we had to find the fourth term using this sequence, we'd have to use n as 3, or the 20th term n as 19, because 0 to 19 gives you 20. So let's have a look at number 1. Use the recursive formula. There's A1. Now we're going to substitute into there to get A2. Now we know A2. We're now going to substitute that to get A3 and a further substitution to get A4. And that's the recursive formula, using the formula. Let's have a quick look at this and use the formula to see what it gives. So there's our formula. Notice I'm using 3 to get the fourth term because the formula starts with x0. So when n is 3, we have 4 terms. And yes, there we are. It gives us 16, so therefore the formula does work. We've confirmed it for this recursive sequence, but in fact it is a first order linear difference equation as well. Now we need to use the solution formula to find the 20th term. So remember, once again, we're going to use n equals 19 to do it. So there we are. We substitute into the formula, and when we solve, quite a large number, 4,718,587. And there is our 20th term. Now, one case where it's used quite a bit is in change of temperature. We're going to use this to illustrate the first order linear difference equations. For example, you could have a cup of tea cooling down to room temperature, or you could have a cool drink warming up to room temperature. There's some parameters. T0, T0 is the initial temperature of the object. That's like the A0 originally, or the A1 of the recursive sequence. S is the constant temperature of the surrounding environment, the ambient temperature it's called, so we'll refer to it as the ambient temperature from now. Room temperature. Tn, the temperature of the object after n units of time. And there's a formula. Tn plus 1 minus Tn, so that's the change in temperature between n plus 1 and n, so that's over 1 unit of time, is equal to some constant k times Tn minus S, the ambient temperature. Now that k is a varying constant depending on the solution that's cooling or the solid that is cooling, and it will vary depending on the substance. This is called Newton's law of cooling. Now, with that k being variable, that's usually the first thing we have to do in Newton's law of cooling, is to determine the k using factors given. So let's have an example. A cup of tea initially 82.2 degrees C in a room of temperature 26.7 degrees, and we're told after 1 minute the tea has cooled to 79.4 degrees C. We need to do that measurement, otherwise we're not going to know the value of K for the tea. What will the temperature be after 20 minutes? Now, what are our factors? We have these three measurements. Tn, that's the initial temperature. Tn plus 1, that's after 1 unit of time, in this case being a minute, it's now 79.4 degrees. And there's the ambient temperature, S. We don't know K. But we're now going to use Newton's law of cooling. If we substitute into there, the only variable we'll have is K, and we can solve for K. It's a pretty straightforward maths equation. We end up with K equaling negative 0.05. Now we have the value of K, we can go back to finding the temperature after 20 minutes, because we now have the full cooling formula. Now, in order to find T20, we're going to use the solution to the linear difference equation. But to do that, we need Newton's law of cooling in the form of a linear difference equation for Tn plus 1, which we can do pretty easily by taking Tn across, multiplying out, and doing some algebraic processes. So let's do that. We start there. We've multiplied out, moved the Tn across, factorized to take out a common factor of Tn, and we now have it. There we are. Newton's law of cooling in the form of a linear difference equation. Now, you will always be given this in an examination situation. You may not be given this, so you may have to be prepared to adjust that to obtain the Newton's law of cooling in the form of xn plus 1 equals Tn plus 1 equals. Now that we know that, we can apply this formula. So here we go. Xn becomes Tn. Alpha, well, alpha times Xn, there it is. K plus 1 times Tn, so therefore your alpha is K plus 1 k plus 1, k plus 1. Your x naught is your t naught, and your beta is that constant there, which means beta is negative ks. We now substitute all the values in, and thank heavens for calculators. 46,6 degrees. So remember what we did? Task 2 was to find T20, but task 1 always is to find K, because we don't know K for all the varying solids and liquids. Here's one. Try this one yourself. Pause and try it yourself first. Very similar to the previous one. First, we need to find K. There we are. We have Tn plus 1, the ambient temperature S, and we need to know K. So we're going to use Newton's law of cooling. We want to write it in the form of a linear difference equation. In fact, we don't need to at this stage. Sorry, we're finding K. So all we're going to do is we're going to substitute those values in and solve for K. And we end up with K equaling negative 0.1. Yes, now the second part is solve the difference equation from part 1. Well, this is where we're going to have to write that in the form of the linear difference equation. There it is there from the previous time. You can very simply go through the algebraic process to see how we get there again. And there is the solution into the actual formula. Substituting the values we know, there we have now solved the difference equation. When we're told solve the difference equation, we need to leave n as n, because there you are now. We now have a formula to find the temperature Tn. And that's in a slightly simpler form. Notice this is 0,1, so it cancels with that 0,1. Part C, we now have to find the temperature after 25 minutes. So we're going to find T25. Notice you might say, well, why aren't we subtracting and making it T24 as we did before? Well, just remember that at T0, no time has passed yet. That's why it's like that. That's why we use the zeros. So if we want T after 25 minutes, we'll actually have it at T25, because at T25, 25 minutes will have passed. It will be the 26th term of the sequence, but the first term of the sequence, T0, is at time 0 when nothing has happened yet. So there's our equation, our solution, and we can now substitute in. We need to find it 25 minutes, so we can substitute 25 in, and we're straight at 24.9 degrees. Next part, find the limit of Tn as n tends to infinity. Well, we're going to look at this, and we're going to say, well, 0.9 to the n, anything less than 1, between 0 and 1, well, negative 1 and 1, to the n as n tends to infinity goes to 0. So that's going to go to 0, and that's going to go to 0. Notice there's the 0, 1 minus 0. And that simplifies to 21.1 degrees. So there's the limit as n tends to infinity. Now question E says, will the coffee reach room temperature? Well, theoretically no, as it's a limit. So N is never going to reach infinity. It'll get very close, as close as you like, but it'll never ever get there. So what this says in theory is that this cup of coffee will never ever get to 21.1 degrees. It'll get as close as you like. Realistically, we know that it will reach room temperature because there are other parameters as well. So yes, in the real world. Just remember that mathematical modeling isn't the real world. We fix parameters. But mathematical modeling, you can get as close to the real world as you like by introducing other variable parameters. So you might say, well, this is highly theoretical. Yes, it is at this stage, but it becomes less theoretical the more parameters you introduce. Now we have a cooling question. But notice there's something missing here. We have the temperature initially, after 1 minute 10 degrees, and after 2 minutes 12.2 degrees. I'm not sure if you can see what's missing, but of course is the temperature of the room. Here's what we have. T0, the initial temperature, T1 after 1 unit of time, T2 after 2. But we don't have the ambient temperature, and we don't have the value of K. There are two variables we don't know. So how do we go about solving for two variables in maths? We use simultaneous equations. So I'm going to use Newton's law of cooling to form two simultaneous equations. We can have from T0 to T1, and we can have from T1 to T2. So first equation from T0 to T1. Here we are, we're applying Newton's law of cooling. We don't know S, we don't know K, so we have two variables there. So there's our first one. Now we can use T1 to T2, and that gives us another equation. Now we're going to have to find either K in terms of S or S in terms of K from one of the equations and substitute into the other. I think it'll be easier to find S in terms of K, so let's do that. Move Ks to this side, 2,8 subtracts there, divide by the K. We end up with that. There's your value of S. Now we're going to take that and we're going to substitute it for S there. So 10K minus K times S times that equals 2.2. And solving, we get K equal to negative 0.214. Knowing that, we can now go back and substitute into there to find the value of S, the ambient temperature. And there we have it, the ambient temperature, 20.3 degrees.